All right. Welcome, everybody. My name is Suresh Srinivasan. I'm the coordinator for the Beginner Special Interest Group for the Minnesota Astronomical Society. Today, we're going to have an awesome talk by my good friend Claire Weaverling on globular clusters. Before we get started on that, though, I want to invite you guys to another talk our new president, Vols Triberg, is going to do tonight for the Cedar Rapids Astronomy Club. Vols, you want to just chime in here and just do a quick plug on it?
Yeah, so I added a Zoom link in the chat. It is at 7:30 p.m. It's free. Anyone's welcome to join in. It's essentially a rehash of the same talk. It's the same talk that I gave to the MAS back in July about the University of Minnesota Students Practice Observatory and the equipment and all the restoration that I have done. And there is a couple of slides that are updated from the talk in July, but feel free to join us.
Awesome. And thanks for doing that, Vaults. Let's get started. So Claire is become one of the super observers our entire club. She has an 18-inch obsession, I believe, right?
Yep, correct.
Dobsonian
Yeah,
that she loves to use, and she brings it to. She's usually a CGO, a Cherry Grove
but yeah,
Observatory, and she's normally doing an astronomical league list that you can find her doing. So she's become quite the visual observer in the past few years. So I was excited that she agreed to do this talk on globular clusters. So with that, I'm going to turn it over to Claire.
okay. I just want to do a check. You all can hear me fine, and you can see my
Yeah,
PowerPoint, right?
I can. Oh, Claire, let me do one thing.
Yeah,
If anybody has a question, please put it in the chat. If you go to the bottom of your screen, you'll see a chat button. Click on that, and a box will open up on the right. Just type your question there. And then what'll happen is when Claire pauses, I will read the question to her. This helps with so she can keep her flow.
mhm.
And at the end, we'll have another Q&A session that you can just speak up regular for. All
Perfect.
right, Claire, all yours.
All good. Okay. The title of my presentation today is Globular Clusters and Why They're So Cool. I liked this quote, understanding the physical processes behind the formation and early evolution of globular clusters is one of the most fascinating and debated astrophysical questions of the past 20, 25 years. So hopefully as part of the beginners group, you've had the opportunity either through your own equipment or through loaner scopes out at Eagle Lake or out at Metcalf as part of the BSIG, you've had the opportunity to observe some globular clusters. If you're a visual observer, you might, and there's some pretty spectacular globular clusters that most of us have seen before, and I'll talk about some of those. But sometimes when you've seen globs, they might seem more like faint fuzzies, and you might think, oh, they all look the same. If you're an imager, I know I've heard I'm not an imager myself, but I've heard imagers say that either that globular clusters are difficult to image well, or maybe not as interesting to image because they're not as cool as some of these big areas of gas and dust right within our galaxy that come in so many different varieties that they're more interesting. But I wanted to take an opportunity today to step back and appreciate the visual variety that is available with globular clusters, but also to step back and think about when you're looking at a globular cluster, what this object actually is and how mysterious and cool these things really are. Let me see here if I can advance my PowerPoint. All right. I think Suresh already introduced my 18-inch obsession. So just a little background on myself. I've been a member of the MAS for about maybe 15 years or something, but very sporadically at the beginning. I joined the club and would maybe show up at ELO or a meeting now and then, but it was kind of doing my own thing. And then it was more recently, maybe about 8 years ago, where I tried to make a point to start coming to meetings on a regular basis and getting to know more people in the club, and then getting more active at coming to the variety of sites that we have and doing more serious visual observing. As Suresh said, I like to do the Astronomical League projects because otherwise I'm sort of out there with my telescope just going, okay, what's up tonight? And then I end up, like a lot of people, looking at the same things over and over. So having an astronomical league project that I can do gives me a focus, kind of gives me a plan, and then it forces me to see some objects that I might not normally think to observe. So yeah, I'm often down at Cherry Grove with my 18-inch Dob working on various projects. I did have the good fortune to be in Texas last April for the total solar eclipse, and I started setting up an imaging rig. So I got a small equatorial mount and a nice Canon mirrorless camera in order to photograph the eclipse. But then once you do that, once you get started on that pathway, then you want to add to it. So I've kind of just dipped a little pinky finger into the world of imaging, and maybe over the course of this next year, I'll try to get more practiced with the imaging.
I should say though, so this scope is Clear Skies.
Correct.
Claire has another Dobsonian called Clairvoyant,
It's
right?
true.
That's your
And
10-inch.
yeah, Suresh named that one. So I started on a 12-inch Dob. That was my first starter scope. And we were in the panhandle of Oklahoma, which I'll mention. And I had my 12-inch at that time, and Suresh, you came up with that name actually, right? Which I thought was quite clever.
Perfect name for that scope.
Mm-hmm. Yep. So then when I got the 18-inch, I'm like, well, Clairvoyant's taken. What do I call my 18-inch? So Claire Skies is kind of what I came up for that. So came up with. All right. So let's start by talking a little bit. I mentioned Astronomical League programs. I'm sure as part of the BSIG, you've learned about these, but I'll just high level mention these are great. There's a variety of projects from beginning, intermediate, advanced, but these are a great way to get started doing visual observing. I had done previously the Messier list of 110 objects and also the Caldwell list. So I had a chance, there's lots of globulars in the Messier, and I had observed many of those before. And for whatever reason, I just kind of always felt partial to globular clusters. And so I decided back in 2021 to do the actual Astronomical League program for this. I do recommend getting the book. It's very skinny, it's not expensive, but it is very helpful. One thing about this program is that you only have to observe 50 globular clusters. Messier is 110, so is Caldwell. You may have heard of the Herschel 400, that's 400 objects. Even the open clusters that I'm currently working on is 150. So 50 globulars feels much more manageable than some of the other projects. So that's one nice thing about this. Also, you have a wide variety to choose from. There are 190 objects listed in this book, and you can choose the 50 that you want to observe. You might think, well, wait a minute, are there even 190 globulars in the Milky Way? We'll talk about that. But you do have the opportunity to observe some globulars that are part of Andromeda or part of the Triangulum galaxies. So it's not just Milky Way, but essentially you pick 50 that you want to observe. You're encouraged to mix it up a little bit. So maybe observing some of those bright globulars that you've seen many times before, but looking at them with new eyes. But also there's a lot of obscure NGC globulars that you might want to try to observe. And then there's even more obscure catalogs like the Palomar or the Terzan. And you have to do 2 challenge objects. You can do more than that if you want, but it does challenge your visual observing skills. And then you do need to determine the concentration class. So you need to sketch it, you need to describe the globular, and then you need to classify it. And I'm going to talk about that classification here in a second. Right, this is not required by the Astronomical League, but I decided to make my project time bound. This is just me. I wanted to challenge myself since it was 50 objects to do it over one observing season. So starting in the spring, and I finished in August, and to just spend a period of time focusing on globular clusters. That was great because when you're doing the Messier, for example, and you're doing one globular and one open cluster and one galaxy, and you're kind of having that variety is fun, but it's also fun sometimes to just be able to focus on one thing. and learn more about that thing. So yeah, I started up at Long Lake in April, and then I think I finished down at Cherry Grove in August. Now, one drawback to doing my project in this manner, having it time bound in that way, was that, I don't know, I did this in 2021, and I don't know if you all remember the summer of 21, but we had a lot of wildfire smoke. There were those days when you were advised to not go outside. If you did go outside, you could smell the smoke in the air, and the sky had that eerie reddish cast that made me feel like I was on Mars or something. But as a result of that, there were some nights when I was out that I had originally intended to do some more obscure globular clusters, and ended up having to pivot and do more of the Messier objects than I had originally intended. To just give an example, this is Messier 4 in the constellation Scorpius. And I had not intended to observe M4 because I had seen this one many times. And the night that I was at Cherry Grove, I had my Palomar list with me. But if you looked at the southern horizon down at Cherry Grove that night, it was just a brown soup of muckety muck. You could barely make out the teapot or the scorpion in the sky, let alone being able to find an obscure Palomar cluster. I should also mention that night it was high winds. It was like 14-mile-per-hour winds or something like that. So I had to take the shroud off my Dob because it was just blowing around. But I was determined to not leave CGO without accomplishing something. So I pointed my Dob at M4 and I started sketching and describing. My Dob kept blowing, so I would sketch and then put it back on M4 and sketch and put it back on M4. But so I did accomplish something, and I'm actually quite glad that I included M4 in my project after all. That's one of the globulars I'll mention several times throughout this presentation because there are many amazing things to say about that particular globular cluster. But I want to touch upon the classification. I'm not sure if any of you are familiar with this, but the classification for globulars is called the Shapley-Sawyer concentration class. And as you can see, it starts with the low numbers being the most dense globular clusters, highly concentrated. And then as you get toward like a 10, 11, 12 globular, those are very loose. And to give you a couple examples here, we've got the top image is NGC 7006, also known as Caldwell 42. This is in the Dolphin, one of my favorite constellations, Delphinus the Dolphin, little tiny. This is one of the most densely packed globulars in terms of classification. So this is a 1. And then the other globular is M71, which is also NGC 6838. And this is in Sagitta, the Arrow, also a little tiny constellation near the Summer Triangle and not too far from Delphinus. But as you can see, this one is very loose compared to the other one. And in fact, there are some of these globulars that are at the looser end of the classification, the concentration class, that were at one point in history actually thought to be open clusters. But then scientists realized that no, in fact, these are just looser globulars as opposed to denser open clusters. I will also mention that this Shapley-Sawyer is named after a couple of astronomers. Harlow Shapley was at Harvard, working at Harvard University back in the 1920s. He's one of the scientists who's credited with using Cepheid variable stars to determine the shape and size of our own Milky Way galaxy and also the sun's position in the galaxy. And he was working with a graduate student named Helen Sawyer Hogue, also working at Harvard. And the two of them, this concentration class is named after the two of them. She actually went on to become an astronomer in her own right, researching globular clusters and also variable stars within globulars, which I will also touch upon here. All right, so that was my project. that I did back in 2021. I had such a good time doing this project that I decided that sometimes I regret it, but I did go on to start observing open clusters. The open clusters project is, I mentioned it's 150 rather than 50, so it's more objects to observe. And open clusters, it might seem weird, but open clusters are actually more difficult. The obscure ones are more difficult to find and classify than globulars, which kind of surprised me. I did do a presentation on open clusters a number of months ago at one of our club meetings. And if anyone's interested in that, yeah, you can go back in the videos and see that presentation. Obviously today we're talking about globulars. But all in all, I got interested in star clusters in general, which kind of led me back to my globular cluster list of 50. So a couple of years after I completed the project, I decided to go online and start doing a deeper dive into some of these globulars. I actually went online and sort of researched every individual globular that I had observed and tried to learn something about each one. This presentation is really comes out of that. And I told Suresh it was great to put together this presentation because it forced me to organize some of my thoughts and notes on globular clusters into something that I could actually share with other people. I should also say that I'm definitely not an expert on globular clusters. So this is my best attempt as an amateur astronomer to kind of match what I myself observed with what scientists are coming to understand about what globular clusters are and what stars comprise globular clusters in the history. Knowing that I was interested in star clusters, there's a member of our club, a guy named Alan Touchberry, who came across this book and brought a copy of it down to CGO one night and said, "Hey, Claire, I found this book. I think you're really going to appreciate it." I went back, got on Amazon and bought a copy of it for myself. This book has been nice because there is really no central repository of like all the research on globular clusters can be found here. If you go online, you find you know, bits and pieces, and you have to kind of piece things together. But it was, even though this book is several decades old and somewhat dated in some regards, it's still nice to have a book that just kind of has anything and everything you need to know about both both open clusters and globular clusters. All right, so that said, let's dig in a bit more. So let's start with what is a globular cluster? So a ball of gravitationally bound stars that represent some of the oldest stars in our universe. As you'll see to the right, that's a globular cluster. The one in the middle is an open cluster, but typically spherical in shape with a core halo structure to them. It turns out that within globulars, some of the heavier stars tend to move toward the center and some of the lighter stars move toward the outside. So they really mostly do have this core halo structure to them. In certain cases, a globular cluster, the core can actually collapse due to the heavy gravity. So sometimes you'll see some of the globulars mentioned as post-core collapse globulars. This doesn't happen to all globulars. Sometimes there's other gravitational forces like binary stars that can prevent them from collapsing. But in general, I think of your classic globular cluster as being, I imagine, like a dandelion after it's gone to seed, but before it's blown off into the wind. That's what we typically think of it looking like. These objects are very stable and very long-lived in terms of the universe. Again, like these have existed for billions of years since the early universe. They can be tens of thousands of stars up to millions of stars. And the typical distance between stars in a globular cluster can be as close as 1 light year away. In the outer part, and in the core, they can get as close as less than a light year, like 1/3 of a light year away from each other. these balls of stars have long since blown off all their gas and dust. So they're really just these tightly bound balls of old stars. And you can contrast that with an open cluster. I should mention that the globular clusters are found not in the plane of our galaxy, but rather outside of our galaxy in what scientists call the halo, and often concentrated toward the galactic center or toward the bulge. And we can contrast this with open clusters, which are within our galaxy in those like molecular clouds of those star forming regions of gas and dust within our galaxy where stars are born. So open clusters are the result of these young stars that have been born and have stayed together in groups of stars within our Milky Way. So you've got the hot young stars that are the open clusters in our galaxy, and the globular clusters that are in the halo that represent some of the oldest stars. All right,
let me pause it here real quick to
Yeah, is
see
there
if
a
there's
question?
any other questions. Let's see. So Ron asked for that book that you had posted, Michael
Yeah.
Hodka's book. It's not on Amazon, but I did find it on a Chamblin Books website, and I put a link to it in the chat for anybody that's interested in that
Okay.
book.
I got it on Amazon, but there might not be any more copies of
Yeah,
it there.
it says it's out of print on there,
Oh, okay. Yep.
but the other website that I posted here seems to still have it.
Okay, awesome.
I don't see, does anybody have any questions? I don't see any other questions in the chat right now. Nope, I think we're good.
Okay, cool. Let's talk about a couple examples of a globular cluster. Hopefully you've had an opportunity to observe these. For those of us living in Minnesota in the northern part of the United States, Messier 13 in the Great Hercules cluster is probably the most famous example. It's a go-to object at star parties much of the time. So this is I talked about concentration classes. This is a concentration class 5, so somewhere in the middle, not too dense, not too loose. And my own observation of this, the last time I observed it through a 10 millimeter, I described it as being very wide, spectacular, with a white cloud at the center and lots of individually resolvable stars coming out from the center like an octopus. Obviously, like that's subjective, but that's kind of the way that I saw it the last time I looked at it. And then another famous cluster among amateur astronomers is one that you actually need to travel south to see. This is when I was on a trip with Suresh down in the panhandle of Oklahoma, and that was the first time I got to see Omega Centauri through a telescope. I've since had the opportunity to go back to Texas 3 times, and each time I've been there, looked at Omega Centauri. And every time I look at it, I'm impressed all over again. Maybe some people will disagree with me, but I think of all the things you can look at through an eyepiece on an amateur telescope, this has to be one of the most phenomenal things. So you can see the snapshots I have here showing the night sky. These are taken from Stellarium. I think Ron did a presentation of Stellarium last month. So I've used Stellarium to kind of show you where in the night sky, if you were down in Texas in April, about 11 o'clock, 12 o'clock at night, this is what the sky would look like. And right due south, slightly above the horizon, is where you would find Omega Centauri. This one is also sort of somewhere in the middle. It's a concentration class 8, and it appears to us at apparent magnitude 3.9. Okay, I mentioned I wasn't an imager, but since I was down in Texas and I had my imaging rig ready to go for the eclipse, I couldn't resist pointing it at Omega Centauri and trying to get an image of it. So this is my attempt to image Omega Centauri with a 200 millimeter zoom lens on a Canon mirrorless camera. I should say this image doesn't do it justice. This is an object where through the eyepiece, it actually looks much more spectacular. than this image, but this was a nice souvenir for me of my Texas trip. All right, so let's talk a little bit about, I'm not going to go too much into the history of globular clusters, but just sort of bird's eye view. There are a handful of globulars that include M13 and Omega Centauri that I just mentioned, but also Messier 22 in Sagittarius and 47 Tuscany, which is one that I don't know much about and haven't had the chance to observe. You need to be in the southern hemisphere to see that one. But these would be naked eye in dark skies. So that means that the ancients were surely able to observe these objects. We don't really know what they thought about them. Ptolemy was the only one to actually catalog one of these, and he cataloged Omega Centauri as a star. But many centuries later, with the advent of telescopes, starting in the 1600s, when astronomers were starting to comb over the sky with telescopes and catalog the things that they saw there, we get the first, quote unquote, official discovery of some of these globular clusters. So Edmund Halley of Halley's Comet fame is credited with this, the first quote unquote discovery of both M13 and Omega Centauri. We also get some of our comet hunters, so people like Charles Messier and who's the other one? A couple from, I don't speak French, so I'm bad with French names.
Oh,
Lacaille, Lacaille, is that how you say his name?
Lacaille, yeah.
Yeah, who is cataloging objects in the southern hemisphere, and then a guy named
Pierre
Machane.
Machine.
Machine, is that
Yeah.
how you say it?
Yeah.
Okay, I was saying
I don't
Machine.
know.
I don't know, right?
I don't speak French either.
Right. Some of these guys who were either cataloging objects in the southern hemisphere or like Charles Messier, they were hunting for comets and then cataloging everything that wasn't a comet. You'll see some of these names credited with discovering globulars. And then William Herschel is the other guy. Obviously, this is a name we've all heard in the history of astronomy. I think he found something like 3,200 different nebulous objects that are credited to him. But a lot of he discovered a lot of globulars. He's also one of the first guys to sort of speculate on the nature of globulars and get it partially right. So he was able to show that they really do have this kind of spherical shape and this kind of core halo structure. So all in all, over half of the globulars that we know today were discovered by 1800. And then when we get to the end of the 19th century, all of the NGC objects were known. When you get into the 20th century, then you start getting into some of the more obscure globulars, like in 1955, George Abel created the Palomar catalog. We mentioned that that's much fainter, more difficult to find globulars that are obscured by some of the gas and dust in our Milky Way. And then astronomers continue to discover globulars to this day. I don't even think we know how many globulars there probably are in the universe total. But there's probably more globulars in the Milky Way than we even know, and other galaxies we're continuing to discover globulars. All right, so let's talk about where you might find these objects. I love this. I think I used this image 2 years ago in my presentation. I love looking at this map of the Milky Way. So you've got I don't know if you can see my pointer, but I've put a circle here around our own sun. So
Yeah,
here's where you can see it. Okay, so here's where we're located, about 2/3 of the way out in this Orion spur of the Sagittarius arm of the Milky Way. If you look down here, this is a little bit smaller and harder to see, but you can see the halo here, and you can see these little dots that represent globular clusters. I think in one of the websites I was reading, an astronomer referred to as globulars as kind of fireflies drawn to the light. So I mentioned that not all globulars, but a high concentration of globulars are found toward the galactic center. So it's like fireflies kind of around the center of our galaxy. Here, if you can see the constellations listed, you've got the summer constellations of Sagittarius and Scorpius. I'm sure many of you have been out in the summer and have looked in that direction. If you can imagine it in your mind, you've got Sagittarius, the teapot there, and you've got the Scorpion, and then you've got the Milky Way, you know, that looking like it's coming up out of the horizon at kind of an angle. So when we're looking at those constellations in the summer, we have the advantage of looking toward the center of our galaxy, toward the bulge, and also being able to see off the galactic plane. And so that's where you'll find the majority of globular clusters. In the winter, when you're looking toward Orion and Taurus and the winter hexagon, you're really looking in the opposite direction toward the outskirts of our galaxy and more into the plane of the galaxy. There are some globs out there, and I'll mention a couple of those, but in general, you'll not find as much out there. So really, it's that summertime that is globular hunting season. I still think it's good to talk about globulars in December, and why I picked this topic for this month, because it's a great time to start planning your observing for the coming spring and summer. But that said, there are a couple winter globulars. If you're able to get out and observe, you won't want to miss these. One example is NGC 2419, otherwise known as Caldwell 25. This one is nicknamed the Intergalactic Wanderer. And I think that nickname came about because, again, when you're thinking, you know, it's out on the outskirts of the Milky Way, and it's very far away. It's about 300,000 light years out there. I think it's the third most distant globular cluster. So at some point in time, it was believed to be not actually part of our Milky Way. Turns out that it is orbiting with our Milky Way, but it was thought to not be part of it, and so was nicknamed the Intergalactic Wanderer. I mentioned concentration classes. So this is a concentration class 7, so kind of in the middle. It shines at a magnitude 9. And it's unfortunate for us at our place in the Milky Way that this is actually a relatively faint and difficult to find globular cluster, which is unfortunate because intrinsically speaking, it's actually quite an impressive globular cluster. In fact, it's a full magnitude brighter than M13. And if it were as close to us as M13 is, I mentioned M13 in Hercules, if it were as close as M13, it would appear the size of the full moon in our night sky. One other cool thing about this globular is that we talked about Andromeda having some globular clusters, and G1 is a famous globular associated with Andromeda. This intergalactic wanderer is to some person somewhere in the Andromeda galaxy right now, some amateur astronomer in Andromeda who's looking at their night sky and seeing the Milky Way. This intergalactic wanderer is to them what G1 is to us when we look at Andromeda. So that's kind of cool. Another winter object to get out there and observe is one I talked about 2 years ago as part of my presentation. This is actually part of the winter hexagon. So there you've got Orion, the belt of Orion and the sword, and Lepus, the constellation just below that down on the horizon. You can find M79. This is an 8th magnitude globular cluster. It's about 41,000 light years from us. But this is another one to get out there and observe. Right, so how many globular clusters are there in our own Milky Way? The number that you typically hear is 150, although I think since globulars are continually being discovered over the past couple of years, you'll typically hear like 157 or 158 globulars. I did find one astronomy paper that referenced 200 globulars as part of the Milky Way. And I think maybe that's a speculation on how many globular clusters there might be yet to be discovered. But let's say the Milky Way has somewhere between 150 and 200 globular clusters. We mentioned Andromeda. Andromeda's got more. Astronomers think that Andromeda has as many as 500 globulars. The Triangulum galaxy, another one that you may have observed, that's part of Messier, 54 to 122 globulars associated with that. And then I picked a couple other examples of objects that you might be familiar with if you've seen M81 and M80 and M82 and Ursa Major. That's a popular target for amateur astronomers. That galaxy is thought to have around 210 globulars. The Sombrero in Virgo is thought to have as many as 2,000 globulars. And M87 also in Virgo is thought to have as many as 15,000 globular clusters. So scientists think that all galaxies of sufficient mass are thought to contain globulars, and every large spiral or elliptical galaxy that's been surveyed has been found to have globular clusters associated with it. And even some of these smaller dwarf galaxies that we'll talk about a bit later in the presentation are also have been found to have globular clusters associated with them. So I think it's kind of cool to imagine, again, imagine you're I don't know what beings live in Andromeda or M87 in Virgo, but imagine you're an amateur astronomer somewhere in M87 in Virgo, and you're looking up at your night sky, and depending on your vantage point, you're able to see tens of thousands of globulars in your night sky as opposed to the 150 that we have available to us. So how old? We mentioned that these are some of the oldest stars in the universe. How old are we talking here? Well, the majority of clusters that I think all of them that I had on my list of 50, when I looked up the ages, were somewhere between 12 and 13 billion years old. And the oldest one that was on my list, and also the oldest one the one that's thought to be the oldest, is Messier 92 in the constellation Hercules. This is one of those globulars that I think it suffers from proximity because it's in the same constellation as M13, and M13 is brighter. So M92 is inherently cool, but because it's close to M13, sometimes it's overlooked. But it's quite an impressive globular in its own right. This is a concentration class 4 globular, and it shines at magnitude 6.4. I mentioned the intergalactic wanderer is like 300,000 light years away. That's way far out there. This one is much closer. This is only 26,700 light years away, so still very far, but closer than the other one. And what's interesting about this 13.8 billion year age is that if you're familiar with the current estimate, scientists think that our universe itself is 13.8 billion years. So if you think that this globular and our universe are essentially within the ballpark of the same age, this means that the stars in this cluster go back to the very earliest stages of the universe itself. So going back to when you're looking at a globular cluster and thinking about what it represents, that is quite mind-blowing that you're looking at some of the oldest stars in our universe. The only one that I had on my list that was considered a young globular was this one, Messier 71 in the constellation Sagitta. Again, we talked about this. Here's our summer triangle, Vega, Cygnus, Aquila, and then I mentioned Delphinus, the dolphin down there, and Sagitta, the arrow, is right there off the summer triangle. This one is quote unquote only 9 to 10 billion years old, which is young for a globular cluster. To just give you some points of comparison, when I did my open clusters presentation a while back, I discovered that the oldest known open cluster is Berkeley 17 in Auriga, and that's thought to be 10 to 12 billion years old, which is really, really old for an open cluster. So that kind of puts that open cluster in that really old open cluster in the same ballpark as this super young globular cluster. But that open cluster is a rare exception. In general, most of the open clusters that you see in the night sky are super young in comparison. For example, the Pleiades is only 10 million years old. The butterfly cluster which is Messier 6 in Scorpius, is only 94 million years old. The Hyades, which is the horns of the bull in Taurus, that one is 625 million years old. And the double cluster in Perseus, if you've seen that one, which is a really lovely double cluster, that's super young at 13 million years old. So we're talking about an open cluster that's 13 million years old, and most of these globular clusters that are 13 billion years old. All right, so what are some of the ways that scientists know that these globulars are so old? Well, one thing they can do is look at the number of white dwarfs in a globular cluster. A white dwarf is not considered a star. Actually, it's usually referred to as a dead star, or maybe the embers of a formerly existing star. But these used to be stars that have stopped their nuclear fusion and shed their outer layers, but continue to radiate light from the residual heat within the object. This is kind of the final evolutionary state for lower mass stars, which are actually the majority of stars in our universe. But the rate at which these white dwarfs cool and become less luminous is well known by scientists. So scientists can look at a globular cluster and look at the white dwarfs within it and compare those to a theoretical model they have of the cooling of white dwarfs, and can figure out the age of the globular cluster. So I mentioned Messier 4, the one I sketched in the wildfire smoke and high winds. This is an example of a globular that's thought to have about 100,000 stars, and 40% or 40,000 of those stars are thought to be white dwarfs. While we're talking about M4, I should mention that this is a concentration class 9, so this is toward the looser end of the spectrum, and it's very close to us in globular cluster terms. So again, that intergalactic wanderer that was 300,000 light years away, this one is only 6,000 light years away from us. So this one is very close. This is large, bright, easy to find. This is a great object for beginner observers to try to find. You can jump right off of the bright star of Antares and find it quite easily. All right, another type of old star that astronomers can look for in a globular cluster that tells us that these are really old objects is something called an RR Lyra variable star. So these are old low mass stars that are around 10 billion years old. I'm going to pause for a moment and talk about this Hertzsprung-Russell diagram. Some of you may have seen this before many times. Some of you, this may be new. So just briefly, there's a saying about stars and stellar evolution where scientists might say mass is destiny. So the mass at which the star is born at kind of tells you how that star is going to evolve for its lifetime. And this is a way that scientists plot out this kind of trajectory of stars, where you've got the temperature at the bottom here, where it goes from hotter to cooler, and then luminosity over here, where it goes from less luminous to more luminous. Here's our sun. So our sun is considered a main sequence star, and this main sequence is sort of the trajectory for most of our average sun-like stars. There's a point here where a star typically will cut off the main sequence and start going into this red giant territory. And in here you find what's called the instability strip, where stars lose some of their stability and begin to pulsate. This is where you find all of the kinds of variable stars. I'm not going to get into like what's happening within the star in terms of temperature that causes the luminosity or the optical brightness to change, but that's sort of what happens. And these RR Lyra stars are one of the variable stars that are commonly associated with globular clusters. They're not only found in globulars, but they're very common in globulars. I should also say about these variable stars that they are standard candles in the way that Cepheid variables are standard candles. So because their luminosity is known by scientists, scientists can then use the inverse square law to calculate the distance. So these variable stars are also one way that scientists discern the distance of globular clusters from us. All right, so that's a lot, but let's just say, so I learned about these variable stars, and then I went back to my list of 50 and went through my list and realized that a lot of the globulars in my list were mentioned as containing these RR Lyra variable stars. And this was the one that had the most. This is Messier 3 in the constellation Canis Venatici. And this is one that is thought to have a very large number of these RR Lyra variable stars, 133 of them at least. So M3 is a concentration class 6 globular cluster. It shines at 6th magnitude. It's about 32,600 light years away from us, but an example of these variable stars. There was only one object in my entire list I could find that didn't contain any of these variable stars, and that was NGC 6535 in Serpens. You can see here's Sagittarius the teapot, here's the Milky Way, here's the constellation Ophiuchus over here, and this one is right off of Ophiuchus. But this didn't have any of these variable stars, and that is considered super rare and uncommon for a globular cluster. All right, so we talked about white dwarfs, and variable stars are old stars, and one way that we know that globulars are old. Another way that scientists know that globular clusters are really old is by looking at the metallicity within globular clusters, which makes sense. So if we think about these stars as forming in the early universe, and in some cases they're thought to have formed before galaxies even formed, somewhere in the proto-galaxy. This was at the point in time of the universe when we didn't have much in the way of the heavier metals. They hadn't yet been fused within the core of stars. And so it's common to see a globular cluster described as either being low in metal or metal poor, low metallicity, with trace amounts of heavier metals sometimes. And so there's two different classifications that you'll see mentioned in association with globulars. Walter Bades was an astronomer who divided up the stars in our universe into two major populations, which goes to, we talked about the hot young stars being in open clusters within our galaxy, and the old globular cluster stars being in the halo outside the galaxy, and that's essentially his classification. So the metal-rich stars in the plane of the galaxy are population 1, and the old stars in the halo are population 2. So you always see globulars listed as population 2 type stars. And then there was an astronomer, Peter Oosterhoff, a Dutch astronomer, who discerned two populations of stars within globular clusters. So you'll see a globular cluster mentioned as either an 001 or an 002 type globular And this is all globular clusters are metal poor. If you see a globular listed as metal rich, that just means metal rich by globular standards, but still really metal poor in sort of cosmic terms. Which gets to the question, when I started going through my list and looking up all these different globulars, I kept seeing globular clusters that were mentioned as having multiple populations of stars, which was surprising for me because I thought of a globular cluster as being sort of this old ball of stars that's been somewhat stable, for billions of years. And how is it that we have multiple populations of stars within a globular cluster? And scientists also, numerous decades ago, also thought that you've got a globular cluster made of old stars, and these stars are thought to have been born together in the same gas cloud. So you would assume you would find one population of stars within a globular. But as scientists have surveyed individual globular clusters, the majority of them actually contain multiple populations of stars. And we'll start to get into why that might be. When I looked at my own list, I could only find one globular in all 50 that was thought to contain one stellar population. And that was NGC 6366 in Ophiuchus. There was one other one that had some second generation stars in the core of it, but most of the globular cluster was composed of first generation stars, and that was Messier 53 in Coma Berenices. But every other globular that I observed fit this pattern that scientists have discovered of globulars having multiple populations of stars. So there were two globulars in my list where I could find actual research papers by scientists where they describe these populations of stars. So here's a quote about this globular cluster in Ophiuchus. So scientists found tentative evidence for the spread of the elements magnesium, silicon, and zinc, indicating an enrichment scenario where the ejecta of evolved massive stars of a slightly older population had polluted a newly born younger population of stars. And then another one here in the constellation Sagittarius 6553, where scientists said, according to the astrophysics data system, a study using the apogee survey has revealed the presence of two distinct groups of red giant stars within the bulge globular cluster, each exhibiting different chemical compositions, indicating a complex star formation history within the cluster with potentially multiple episodes of stellar enrichment. So I thought this was interesting, that it sort of dispelled the image I had of globulars of being sort of just singular balls of old stars. It turns out that there are lots of interactions that happen to globular clusters. Interactions from without, where globular clusters encounter something in their environments that cause these perturbation of events. Also, there are dynamic encounters that can happen within globular clusters, since these are tightly packed balls of stars that can produce some unique stellar types of stars. So let's start with, I want to start with this idea that a globular cluster can have multiple encounters from without that might disturb the original population of stars and cause a globular cluster to either lose stars or gain stars somehow. So a lot of globular clusters in our Milky Way are thought to have not formed actually with our Milky Way galaxy, but are actually globulars that we've picked up from various collisions and mergers of our galaxy with a dwarf galaxy in our vicinity. One paper I saw broke it down into about 40% of galaxy, or 40% of globulars are thought to have formed along with our own Milky Way, but as many as 60% of the globulars that we see with our galaxy were actually picked up from a collision with a dwarf galaxy. And so I went back to my list of 50 globulars, and sure enough, quite a number of them were associated with various dwarf galaxies. One that you'll see mentioned quite often is the Sagittarius dwarf elliptical galaxy. Sometimes it's also referred to as the Sagittarius dwarf spheroidal galaxy, or just the Sagittarius dwarf galaxy. But M54 is an example of a globular cluster that scientists think actually wasn't originally part of our Milky Way. It's something that we've picked up from this dwarf elliptical galaxy. And in fact, some scientists hypothesize that M54 is actually the core of that dwarf galaxy. If you've had an opportunity to observe M54, it is a concentration class 3. It shines at an apparent magnitude of 7.6 and is about 50,000 light years from us. Another one, let's go back. Sorry. Let me go back. There are a handful of other globular clusters in Sagittarius that are more obscure. I mentioned like the Terzon catalog. There's a couple more obscure globulars in Sagittarius that are also thought to comprise the main part of the Sagittarius dwarf elliptical galaxy. But as that galaxy has collided with our galaxy and interacted with our galaxy, it's also obviously left behind kind of a trail of what I think of as being sort of a trail of debris. And there were other globular clusters I observed that weren't part of the main core of that dwarf galaxy, but rather were part of what scientists call the Sagittarius stream. And so NGC 56 and 34 is an example of a Sagittarius stream globular cluster. This one is a concentration class 4 globular, and it shines at an apparent magnitude of 10. It's about 82,200 years ago. 82,200 light years from us. All right, and yet another dwarf galaxy associated with some of the globulars that I observed is one called the Gaia sausage. This has kind of a strange name. It's named after the Gaia ESO star survey, which I think the Gaia project is the European Space Observatory, right? So this was one of their projects that detected this dwarf galaxy, and it's called the Gaia sausage because apparently a lot of the stars associated with this dwarf galaxy have highly elongated orbits, which when you plot them out on a velocity chart actually make kind of the pattern of a sausage. Therefore, it was dubbed the Gaia sausage. But M56, one of the globulars that I observed in the constellation Lyra, so again, part of the summer triangle here, this is thought to not have originated with our Milky Way galaxy, but rather to be the remains of this dwarf galaxy that's thought to have collided with the Milky Way some 8 to 11 billion years ago. All right, so there's yeah, go ahead, sir.
Let me just pause you for a second. Does anybody have any questions? I haven't seen any come through the chat, but this would be a good time to ask a question if there's one out there. Don't see anything coming through.
All right. I'll keep plugging away, and then at the end, if anybody has anything, we can circle back to any of these slides at any point. So in a nutshell, a lot of these globular clusters that you see have actually undergone a number of perturbations and dynamic interactions in their history that have caused them to gain or lose stars and develop these multiple populations of stars within the globular. I found this awesome visual from the Encyclopedia of Astronomy and Astrophysics at Caltech that kind of shows you, here's our Milky Way. And you can see that a lot of these globular clusters, there are globular clusters that orbit with the Milky Way that are considered disk globulars. They rotate with our galaxy. But in general, most of these globulars have, most of these globulars are moving much faster than our sun and have these highly eccentric elliptical orbits that are different from the rotation of our own galaxy. Typically, a globular cluster, it takes a globular cluster about 100 million years to do one of these orbits on average. But you can see where as the globular clusters are orbiting, there's lots of opportunities for these globular clusters to either collide with one another or be perturbed by the gravity of our own galaxy, or pass through the disk of our galaxy and be perturbed by these various forces. So when I looked back to my list of globulars that I had observed, I found many mentions of these kind of perturbations. So to just give one example, this one was kind of weird because when the night that I observed Messier 53 alongside NGC 5024, I actually logged them together. They're 1 degree, they appear with only 1 degree of separation visually. So I observed them together and actually logged them together on my log sheet, but didn't actually realize until later when I went back and researched them that they were actually gravitationally, they weren't just next to each other visually from a visual point of view, they were actually interacting gravitationally with each other. And this was really interesting. An interesting example of two globular clusters actually colliding with one another. And in fact, scientists think that Messier 53 is actually stripping stars away from this NGC 5024. And that's what, whoops, sorry. That's what scientists refer to as a tidal star stream, or sometimes a tidal bridge. So as the one globular strips stars away from the other globular, it forms this tidal bridge. Unfortunately, this particular tidal bridge, the stars that make up that bridge are 23rd magnitude or dimmer, so it's not anything that you can see visually. But it's kind of cool to think that that's something that's happening. Another example of these perturbations, this is NGC 5466 in the constellation Boötes. And this is one where scientists think that there's a tidal stream. You can see the object right here. Scientists think that there's a tidal star stream that goes from Boötes all the way over to Ursa Minor, or sorry, Ursa Major, and that is being caused by this NGC 5466. This is something that was picked up by the Sloan Digital Sky Survey. And this is an instance where they think that this globular cluster is being perturbed by the actual gravitational tug of our own Milky Way galaxy. Another example of this is we're going back to M4, which I've mentioned several times in this presentation. So M4 in the constellation Scorpius. This is an example of one of those globulars from that picture that I showed that's actually that actually, as it orbits the Milky Way, passes through the plane of our galaxy. It's thought that M4 has passed through the plane of our galaxy multiple times. And each time it does that, it experiences this tidal shock and is disrupted enough that it sheds stars. So astronomers think that at some point in the far distant history, M4 had many more stars than it actually does today. But as it's undergone these repeated tidal shocks, it's actually shed stars. And then another example of this is M2 in the constellation Aquarius, Messier 2. And this is another globular associated with a tidal stream. In this case, they think that Messier 2 is being perturbed by gravitational pull from the Large Magellanic Cloud. M2 is another globular that is hypothesized to be a remnant of a dwarf galaxy, namely the Gaia sausage that I mentioned. So it's kind of cool to think that M2 actually came to us from a collision between the Milky Way and a dwarf galaxy. That's how it came to us. And it's now being perturbed again by gravitational pull from yet another galaxy, which is the Large Magellanic Cloud. And in fact, astronomers think that at some point in the future, maybe 10 billion years in the future, a certain percentage of the globulars that we see today won't exist anymore because they will have been pulled apart by these sorts of dynamic forces that they're subject to. Right, so that kind of gives you I know that was a lot of information, but that kind of gives you an overview of some of the forces from without that can interact on globular clusters and cause some of the visual differences that we see and some of the differences in populations of stars. I also mentioned that because globular clusters are so densely packed that the stars within a globular cluster can have interactions with each other, and this can produce some really interesting and unique stars within globular clusters. And one example of this is a star called a blue straggler. So going back to our Hertzsprung-Russell diagram that we looked at before, here's the main sequence stars, and here's the turn-off point where a sort of typical mass star like our sun might turn off the main sequence and become a red giant. However, some of these blue stragglers within globular clusters don't do that. They actually continue on up into this quadrant here where they become more luminous. They become cooler but more luminous. And the only way that that could happen is if these stars are somehow, I mentioned that mass is destiny. The only way this could be happening is if these stars were somehow acquiring mass. And sure enough, I came across a research paper by a group of scientists in India who looked at this and determined that sure enough, these stars are having interactions with other stars and picking up mass. And so there were 3 different ways that a star can do this. One way would be that the stars become companion stars and one companion transfers mass to the others. There could be a collision of 2 stars where mass is transferred, and then there could be interactions of multiple stars, more than 2 stars, where mass could get transferred to a star, and then instead of going off the main sequence, it could end up here as a blue straggler. So this was really interesting because I saw this mentioned a lot in my list of globulars. There are quite a number of globs that I observed that contained a high amount of these blue straggler stars. And so one example of this is NGC 4147 in Coma Berenices. This globular is thought to contain 23 known blue stragglers. I'll just mention too that this was one of my challenge objects. This NGC cluster is more difficult to find. It's relatively small and dim. It's a concentration class 9 globular, and it appears at 11th magnitude. It's about 60,000 light years away from us. There's another one in Coma Berenices, which was also a challenge, one of my challenge objects. This is a concentration class 11, a 10th magnitude one, also extremely faint and small, about 60. This one's about 57,000 light years from us. And this is another one that's thought to contain about 27 of these blue straggler stars. Another interesting kind of star that you'll find inside a globular cluster, inside some globular clusters, not only found in globulars, but highly associated with globulars, is a type of star called a millisecond pulsar. These pulsars are super, let me start over. These pulsars are super fast, are pulsars with super fast spin that are thought to be old, rapidly rotating neutron stars that have been spun up again by the presence of a nearby binary companion star. So let me kind of go through that again. So in general, a pulsar is a rapidly rotating neutron star. It could occur, let's say, a very massive star that explodes as a supernova and then becomes a pulsar. Typically, when this occurs, a pulsar can last from 10 to 110 million years, but eventually it will slow down and turn off and become a cooling neutron star. That's typically what might happen. But because of the density within globular clusters, if you have one of these exploding stars that turns into a pulsar, but it happens to be in close proximity to other stars and pick up a companion star, even a companion star like kind of a normal sun-like star, eventually that sun-like star, when it becomes a red giant, will begin to expand and then will cast off some of its matter onto this pulsar and then spin up the pulsar all over again and start the process all over. These kind of millisecond pulsars not only are very fast, but scientists think for some reason, these super fast pulsars have much smaller magnetic fields than other pulsars. For some reason that scientists don't fully understand. But this tremendous combination of tremendous spin with a smaller magnetic field can cause them to last forever. So they'll just keep on spinning into eternity, as opposed to other kinds of pulsars, which will eventually wind down. So this really super interesting kind of pulsar, I think there have been 3,000 of these kinds of pulsars, millisecond pulsars discovered, and about 5% of those are found within globular clusters. I mentioned at the very beginning 47 Tuscanae as the globular cluster in the southern hemisphere that I've never had an opportunity to observe, but that particular globular cluster is thought to have about 25 millisecond pulsars within it. Unfortunately, that one wasn't on my list, but Messier 5 was one that was on my list. And this one is thought to have, I think there's 2 millisecond pulsars within M5. Okay, and I'm almost toward the end here. I've got just a couple more things to mention. Black holes is another thing that you will find within a globular cluster. I'm not any kind of expert on black holes, but my understanding of black holes is that you can have a stellar mass black hole. You can have anything from a stellar mass black hole on up to a supermassive black hole, with a stellar mass black hole being more like something you might find if an individual star explodes as a supernova and then eventually forms into a black hole, or a supermassive star just collapses into itself and can form a stellar mass black hole. That's different than the supermassive black holes that you find at the center of galaxies, where you could have multiple black holes that merge with each other or eat up a lot of the matter around the black hole and become more and more massive. There's something called an intermediate mass black hole that's kind of would be in the middle of those two things. And scientists consider that kind of the missing link between a stellar mass black hole and the large massive black holes that you find at the center of galaxies. And a globular cluster is one of the places where scientists have been hunting for these intermediate mass black holes. The slide I have up here is M22 in the constellation Sagittarius. This is one of the ones that I observed that had only 2 stellar mass black holes within it. But I had mentioned Omega Centauri at the beginning when I was down in Texas. And over the past year, in 2024, there were 2 different research papers that were produced by scientists where they found evidence for one of these intermediate mass black holes in the center of Omega Centauri. So that's kind of cool to be finding black holes within globular clusters. And then there's only one other phenomenon that I wanted to mention briefly, and then I'll wrap this up. On Thursday night, we had a great presentation at our club meeting by a woman from the Jet Propulsion Laboratory in California. She did a presentation on exoplanets and the search for exoplanets in our universe, and the Nancy Roman Space Telescope that will go up in orbit in a couple of years. Well, I wanted to mention that there is one exoplanet that's been found inside a globular cluster. Again, M4, which I've mentioned several times over, Messier 4 and Scorpius is thought to contain one Jupiter-like exoplanet. This is kind of cool and significant because it's the only exoplanet so far discovered within a globular cluster, but it also demonstrates that it's possible for there to be a planet within a globular cluster. Scientists think that terrestrial Earth-like planets are probably not possible, but a planet like this one that's 2.5 times the mass of Jupiter is obviously possible. Also, it's the oldest known planet discovered in our universe. And that's also kind of cool. I have this fun cartoon that I found online that sort of summarizes several different things we've talked about together. Thought this was interesting. I'm actually just going to kind of read through this. So you've got a Jovian planet that forms around a sun-like star in the outskirts of M4 about 13 billion years ago. This planet travels to the core. We mentioned that stars tend to move, if they're heavy enough, move into the core of a globular cluster. Because stars are in close proximity to each other, this star passes through M4's core and is drawn toward a neutron star and its companion. So one binary system encounters another binary system, and the slowly spinning neutron star captures the star and the planet, spinning out the original partner star into space. The sun-like star then swells to be a red giant, spilling its matter onto the neutron star, as we talked about. And then this neutron star spins up, becoming a pulsar that spins 100 times a second. And the red giant becomes a white dwarf, like we talked about. So then you end up with a Jovian planet that continues to orbit relatively undisturbed around this new binary system. So I thought that was cool because that kind of summarizes some of the interesting interactions that can happen within a globular cluster. So I feel like that was like a ton of information that I just shared with you. I'm going to leave it there, and then we can open it up to any questions or discussions that any questions or anything that any of you want to add to the discussion. This experience of observing globulars was for me, one of my favorite visual projects that I've done so far. And then I really enjoyed taking a deeper dive into these amazing objects. My very first night working on the globular cluster project, I was up at Long Lake Conservation Center with Trina, and Dill Prickles, who's the porcupine who used to live up at Long Lake, and we found out he recently passed away. Dill Prickles came walking right through my observing site that night. So I just wanted to end on this slide to acknowledge Dill Prickles. And it was cool that I got to have an encounter with him the night that I started my globular cluster observing. So with that, I'm going to leave it there.
Yeah, this is great, Claire. Thanks for doing this. Chris Setness has a question. Do globular clusters themselves have spin? If so, does that affect their shape? They are very old, so do they get tidally locked to the galaxy's core?
Oh, that's a good question. I actually don't know the answer to that question. I know that they have they tend to have retrograde orbits around the core of the galaxies, but whether the globular clusters themselves have spin or are tidally locked, that's a good question and something I would have to research that I'm not sure about. If there's anyone else on the call who has an idea about that, definitely chime in.
I would guess yes, especially the ones that you'd mentioned that have interactions.
Yeah,
that would definitely impact their spin and their orientation. For
right.
Sure. Great. Any other questions out there? If you want to just ask it yourself now, you don't have to use the chat. While we're waiting for questions, I'll note that if you guys look in the chat, Claire had mentioned the Astronomical League programs early on in the presentation. I put a link to their website. If you want to see at 1:07 p.m., I put a link to the Astronomical League observing programs, and then also specifically to their globular cluster observing program, in case you're interested in seeing that and what that all entails. Claire, did you want to add anything about the actual observing program for globulars? Did you want to add anything to that?
I kind of touched on that at the beginning, what it entails and how I approached it. Was there anything, Suresh, anything else you think I should add?
No, I just wanted to make sure that we covered it. That's all.
I can, if anybody jumped on late, I can mention it again. It was,
Sure,
I mean, as you've probably gathered from this presentation, it was my favorite project so far. It's 50 objects, and you get to choose from 190 objects total, and you get to include some challenge objects, which includes more obscure globulars, but also maybe you want to try observing some globulars of other galaxies. So that's cool.
Very cool. Thanks. Alan, you want to chime in?
Yeah, I was just going to ask. I joined late, sorry. So if you already did all this, forget about it. But what kind of resources beyond the Astronomical League have you found? Maps, charts, books, whatever, to help you with your quest for globular clusters?
Yeah, so I would say there are 3 things that I used for this presentation. Alan, I don't know if you were on at the beginning. I mentioned your star clusters book. Did you?
Oh, okay. All right. Yeah, I missed the beginning, so I'm gonna have to watch it when it gets posted to YouTube or someplace.
So one reference that I used was your book that I mentioned, and I think Suresh put a link to where you can purchase that book if anybody else is interested. I kind of talked about it.
That's the Hot Cup book, right?
Yeah.
Yeah, Alan, if you look at 1:15 in the chat, 1:15 p.m., you'll see the link to that book.
Okay, thanks.
So yeah, that was one reference I had. So I said there's kind of 3. One was the book itself. And I also mentioned at the beginning, Alan, that there's obviously online, just Googling things and trying to find, scientific, the mix of stuff that's online. You find a mix of, articles that are written for popular astronomy that, and also science articles, science papers themselves. So kind of a mix of that stuff you find online. There's no central repository for everything about globulars. So I really had to do a lot of like online digging, as well as referring back to that book, as well as, I forget the name of the astronomer, and we might have it in our great courses. I'm not sure if it was one of the great courses with the Loner Scope program, but there was on my Roku player on Wondrium, there's a class on the evolution of stars by a astronomer from Vanderbilt University. I also did that course and took a lot of notes from that. So some of what I got was from that class, some of what I got was from the book you mentioned, and then a lot of what I got was from a bunch of stuff I found online. I do have links to some of the stuff I found online. I have it right now, it's just in a mess on a Word document, but I could organize it and post some of the interesting links as a Word document if anyone's interested.
Good deal. Are there any other questions or comments out there for Claire?
Hey, this is Andy.
Hey,
just
Andy.
number one, let me just say, excellent presentation, Claire. Really appreciated it.
Oh, thank you. I was worried it was like, I don't know, it was hard to organize it and it may be too much information, but
No, I
that's
think you covered the waterfront very, very well.
okay, good.
I got one question for you. Since you're observing with an 18-inch, have you in fact observed G1?
Okay, so my story about G1, when we were up at Long Lake, was it 2 years ago Bob King did the G1 presentation? Does anyone remember?
It's been a couple of years, I
It
know.
might have been 3. Well, no, if it was in 2021, it would have been 2021, the year I was doing this project. So I didn't have G1 in my original list of 50 in my plan, but after attending his presentation, I just decided on a whim to go outside and spend a couple hours trying to find G1, which I did. I don't know if I found it actually. I probably found it, but I spent a couple hours hunting for it and wasn't actually 100% sure what it should look like and what I was actually looking for. I hadn't really done a ton of research ahead of time, and then I kind of gave up, but I still have it on my bucket list to go back. I think there's I wrote it down, there's actually 29 Andromeda globulars that are part of that Astronomy League book.
Yeah,
There's,
less than magnitude 16. Yeah.
yeah, there's 2 of the M33 globulars and 1 of the M110 globs, and then there's actually 1 of the from the Large Magellanic Cloud that's in that list. So maybe one of these days or years, I'll make a point of just trying to find some of the non-Milky Way globs.
Great.
So
G1 is really distinctive because it forms a neat little equilateral triangle.
Yeah,
that
okay.
makes it well identified. Yeah.
Okay, I need to, yeah, maybe talk to you more and make a plan. Right?
So
Very good.
let me just back up for people that don't understand. So G1 is a globular. It's also known as MAL2, and it's a globular of the Andromeda galaxy. What they were just discussing is there are some globulars that are actually part of another galaxy, the Andromeda galaxy, that are visible in amateur telescopes. In the case of MAL2, I believe that's the largest globular known. It's actually bigger than Omega Centauri. So some of these globular clusters, astronomers believe, were actually the cores of galaxies in their formation, and they just never formed a galaxy, or they got too close to another galaxy, got eaten up. And they think that MAL2 may be one of those that's really the core of a former galaxy that just never formed properly.
Right.
That's out there. It's
I
about
also
2.5
mentioned
million
that
light years away.
intergalactic wanderer back at the beginning, like what G1 is to us when we look at Andromeda. If you're I don't know what beings live in the Andromeda galaxy, but if they're looking at us in the Milky Way, that intergalactic wanderer sort of is to them what G1 is to us, which I think
It'd be kind of amazing to be out there, wouldn't it? To be out
right.
that far away and looking back at us and getting to see the whole galaxy and
Yep.
all the stuff that we don't even get to see. That'd be kind of cool.
Mm-hmm.
Do we have any other questions or comments for Claire? I don't see anything in the chat. All right, I guess we'll leave it there. Thank you so much, Claire. That was awesome. So a couple comments. We're gonna have this presentation was recorded, and in a few days I'll have it posted up on our MAS YouTube channel. So if you missed part of it or want to watch it again, you can certainly do so. Our next beginner special interest group presentation will be on Saturday, January 11th at 1 o'clock. That's when Bob King will be presenting on Aurora Borealis, or auroras in general. It's a hot topic now since the sun is at solar maximum and we're getting all this auroral activity. So please be sure to tune in for that one. The link will be on the MAS Beginner Special Interest Group Forum website shortly. So with that, we'll leave it there. Thank you guys for coming, and we'll see you next time. Thanks, Claire.
All right. Yeah. Thanks, everyone. Have a good weekend.
Goodbye.
All right.
Bye-bye.
Bye.